Hi everyone, welcome back. We're going to go ahead and finish up vectors today. So it's section 7.3, once again, vectors in the plane, day 5. Today's essential question is, how do I use vectors in velocity type problems? So what you see in front of you is actually the difference between speed and velocity. A lot of us kind of mix those two up together. So speed refers to a scalar quantity that refers to how fast an object is moving. And it says there it can be thought of as the rate at which an object covers distance. Velocity, on the other hand, has to be represented by a vector, and it's a vector quantity that refers to the rate at which an object changes its position. So if something has a higher velocity, it's further away from its original position, and it's probably doing it at a quicker rate as well. The emphasis for velocity is especially on direction, so north, south, east, west, northeast, anything like that. That's where velocity really differs from speed, because something can have a speed of 5 miles per hour but really not do anything. And the book kind of uses an example in which some object might be going back and forth like crazy, and it could be doing it super quickly, like at 55 miles per hour, just bouncing back and forth between a wall. However, because it's not really covering any distance, it's just going back and forth to its original position, it has a high speed, but it doesn't have any velocity. Velocity has to have a direction in which the object is moving away from its original position, and that's what we're going to see in our examples coming up that are going to have to do with airplanes. So, the first one we're going to do is example 1. We're going to be finding the component form of a vector. And what's given here is that the velocity of an airplane actually, my mistake there. What we're going to be finding is the component form of the velocity, but what we're given is an airplane descending at a speed of 100 miles per hour. At an angle of 30 degrees below the horizontal. Okay, so we're going to be finding the velocity vector for this airplane based on what's given here. It's also going to be based off of this image here, because technically 30 degrees below the horizontal could also refer to us being in the 4th quadrant. However, we are going to be focused here in the 3rd quadrant with a direction angle of 210 degrees. So let me see if I can focus this a little better. So definitely sketch that in alongside the problem. So pause if needed and copy that down. Right, so in terms of the velocity vector, what we're going to have to do is basically determine the whole equation in linear combination form using what's given. The magnitude actually has some place in here. It's the magnitude of v times cosine theta of I plus the magnitude of v sine theta of j. Now, you might be wondering, what is the magnitude of v? We're not really given anything about the velocity vector itself. In terms of the magnitude of this vector, it's actually going to be the speed. So let's make that for reference. The velocity vector's magnitude will be equal to the speed. And then just as a reminder, our direction angle is going to be 210 degrees. Okay, so we're going to take all of that and plug it in. So our velocity vector, and again our goal is the component form of it, we're going to plug in 100 times cosine of 210 degrees. And we'll keep the I in there for now. We'll simplify that just a little later. Plug in 100 cosine of 200, or actually sine, sorry, of 210. And again, we'll also just keep J for now. From there, we're going to go ahead and simplify. Cosine of 210, if you refer to your unit circle, should be negative radical 3 over 2. 100 still out there. I plus 100 times negative 1/2 J. Okay, continuing to simplify, we're going to distribute the hundreds in, so we get negative 50 radical 3 I minus 50 J. And by now you should notice that the component form can really just be taken from these two numbers. And this is going to be kind of like my x term, my y term. So here, negative 50 radical 3, comma, negative 50. So from the origin 0, 0, our component form of our velocity vector is going to be this, and that's basically showing how far the airplane has been basically displaced from its original position at 0, 0. And that's what we see here in this diagram. Okay, so again, this magnitude kind of reflects what we had here, the 100 miles per hour. All right, so let's go ahead and move on then to example 2, which is actually going to be a bit more tricky. In this one, I'm going to ask you guys to refer to page 568 in your textbook if you have one. I'm going to ask that you guys copy down this entire word problem as well as these two diagrams. You're going to have to copy them very closely because they do show specific images of what's happening. So as you do that, I'll go ahead and read them out. An airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with a negligible wind velocity. In other words, there's nothing affecting my flight at this point. So I've flown 500 miles and nothing's really happened. There's no wind kind of causing turbulence. But the airplane reaches a certain point in its flight and encounters some wind that's blowing with a velocity of 70 miles per hour. So it's going to basically push the plane a bit because the plane can't completely resist that wind. So it's a velocity of 70 miles per hour in the direction north, 45 degrees east. So as shown in this one. So you can see it pushing it 45 northeast. What is the resultant speed and direction of the plane? Okay, so quite a bit to look over. Again, draw in that diagram, write in the problem. We're going to go ahead and now move in to solving this. So our goal is again to find the speed and direction of this plane. So example 2. We're going to go ahead and move into finding the velocity of the plane alone, and as you saw in the diagram, it was labeled as vector 1. Okay. So vector 1 has a magnitude or speed of 500, so we're going to kind of borrow that information from example 1, where that's going to be our scalar unit. Okay. Now, one thing I do want to point out in here before I do it, work out the problem, is that it says it has a bearing of 330 degrees, and yet in our diagram we have airplane going like at 120 degrees from the 0 line. What we actually need to understand is that when we use the word bearing of some degree, you're actually starting at the 90 degree line. So here we're starting like right on here, and then you're going counterclockwise, so this way, 330 degrees. And yet when we refer to the actual direction angle, we still refer to it as coming from 0, and that's why it's 120 degrees. So let me see if I can make that a little more visual for us. So again, starting here, 90 degrees. It says we have a bearing of 330, so I'm going to go backwards 330. Sorry, wrong way. So starting here at 90 degrees, once again, bearing of 330, I go counterclockwise 330 degrees, so just shy of 360. And that's where my vector will be. But when I refer to it as a direction angle, I still refer to it as coming from 0. So that's going to be 120 degrees. Okay? Make sure to write a question down if you didn't understand that part that well. But let's go ahead and continue on then. So the velocity of the airplane alone from diagram A, it's going to be 500 times cosine of 120, because that's referring to the x value, and sine of 120. Simplify that, we have 500 cosine of 120 will be negative 1/2. Sine of 120 will be radical 3 over 2. So my plane without any wind turbulence has basically moved this much. It's going to be at negative 250 and 250 radical 3. That represents the velocity of my plane without any of the wind turbulence. Now the next part we want to do is look at that little wind vector, that tiny little wind vector that pushed at 70 miles per hour northeast 45 degrees, and it's being added on to where my plane has traveled to. Okay, so V2, the wind, we're going to go ahead and calculate that. So once again, the speed was 70. And then it's going to be cosine of 45, sine 45. Because again, that was the direction that the wind was going in. So that's going to be 70 times radical 2 over 2, comma, radical 2 over 2. So we get component form of 35 radical 2, 35 radical 2. Alright, so cool, we have two different vectors, but what are we going to do with them? What we're actually trying to find is after this plane has made it out so far, and then it was affected by the wind, just a little smidge. Basically, we're asking, where's the plane now? So we're asking, where's the resultant vector after we add the two vectors together? So basically, the airplane plus wind. Which means we are going to do a little vector addition again. So our resultant vector, we'll just call it V, equals V1 plus V2. And yes, you are going to get something a bit complicated. We have negative 250 plus 35 radical 2, comma, 250 radical 3 plus 35 radical 2. Okay, so that is going to result in a component form of where our plane currently is. So negative 200.5 and 482.5. Now, why am I using decimals? And that's because I'm still going to have to do a little more work with this. Because remember, the original question asked us for the speed and direction of the plane. To get the speed of this plane after finding its velocity vector, I have to find its magnitude. So basically, its magnitude is going to require us to use the distance formula. Now, you may keep it as radicals. That's going to give you a more precise answer, but we'll go ahead and use decimals in this case, because it's going to come out to a really crazy number anyway. So our speed at this point is 522.5 miles per hour. Okay, so after you plug it all into a calculator. Finally, we need to use this to find the direction angle. So tan theta will equal 485 or 482.5, the sine value, 200.5, the cosine value. And after that, you do the arctan, just like we did yesterday. It's going to be 110.6 degrees. Okay? Now, how did I get 112.6, not 110? How did I get that when in my calculator tan theta, or actually arctan, sorry. Theta equals arctan. 482.5, negative 200.5. How did I get this when in reality this comes out to be 67.4? Okay? The reason is because we know that we're in the second quadrant, so we actually have to add 180 to it. I believe this should be actually negative. So I have to add 180 to that, pretty much similar to what you guys did on Friday, and that's how we get the 112.6 degree direction angle. Okay? All right, a lot to process. We will be trying out velocity type problems on Monday. It's a combination of everything we've done so far, especially what you tried on Friday using direction angles and all the magnitudes applied to it. Okay? So hopefully this made some sense. Otherwise, go ahead, write down any questions that you have. I'm sure there will be plenty. And have a wonderful weekend.